what you just heard from Nicola is sort of the protocol and the cryptography that's backing DRAND. And we've got a really nice construction there that gives us a lot of good properties. And then we've got a bunch of really interesting use cases and consumers of DRAND. And there's a host of systems challenges in between, which is that it's not simply the unbiasability that we need, although that is clearly necessary, but we also need to make sure that the randomness that's getting generated by this group of nodes is able to reliably get to downstream consumers that want to make use of it. So there's a systems and networking challenge there in between that we had to think about designing and solving to feel comfortable that a DRAND network as it's deployed is something that other production systems are going to feel comfortable using. So this is trying to give a sense of that journey. Next slide. And so really what that problem boils down to in a lot of ways is how do you do this with an adversarial network? And so what I want to do over the next 10 minutes, 20 minutes, is we're going to try and define more specifically the sorts of attacks that we want to include in our threat model and try and get that threat model a bit more concrete. And then I'll turn it over to Alan to talk about the mitigations in the systems design that we put in to allow distributions of DRAND to stand up to those threats. Next slide. And to start though, I think there is a bit of sort of systems design things that we need to go into. Next. So, and skip ahead maybe too, because what I want to talk about first here is the systems piece of how do we go from nodes having it to consumers getting new items of randomness, right? There's sort of two major classes of threats that we need to think about from an adversarial network. One is an off-path adversary. And so this is someone who is not a DRAND node, who is not the consumer, and who is not an ISP or a network in between them directly, but is some third party who just sort of doesn't want randomness to work. So if you happen to just be somewhere totally random on the internet, how are you going to try and make DRAND fail? And the other case is that you are on path, and our primary worry is not so much a malicious node, because the relative, we can fall back to the cryptographic protocol to solve that problem, right? Which is if some node is malicious, we'll have the clients just go to other nodes as well. And if clients are going to multiple nodes, then we can fall back on our assumption from the cryptographic level that a majority of nodes are going to be honest and working correctly. And so by looking at that consensus, we should be able to mitigate bad nodes. And so the real problem that we have to solve is what happens if the direct ISP of a consumer or of some set of users doesn't like DRAND. Okay, next slide. So we are helped in this separation by the DRAND protocol itself. And one more slide here. The random values that we have are immutable. So once a randomness beacon is published for a specific round, it's not going to ever change. And so that makes it easy to cache and means that we can hopefully minimize some potentials for DDoS. The beacons will continue even under some network partition scenarios. So even if there are disconnections of the group members themselves, as long as you've got a threshold in some place, they can keep generating randomness. And as long as any individual group member gets enough shares to generate the next beacon, there can be ways to distribute that. So we have some resilience already at the protocol level that we can take advantage of resilience to partitioning. The random values as signatures of this public key that's been pre-distributed means that each value is self-validating, that a client can by itself in a non-interactive way validate that that value is the value that it expects for a given time period and knows when that value is supposed to happen. The resharing mechanism that we just talked about, that Nicola just talked about, allows the group to transition without changing the underlying key. And so that means that there's no online key validation or revocation process. So there isn't an equivalent of OCSP stapling or any of these other complexities of needing to have either an online interactive validation process or knowing to check that your security has to be updated. And finally, these things are small. Okay, so we've got a bunch of really almost sort of the best case scenario in terms of the randomness values that we're trying to distribute. And so the sort of high level view of the design that we're going to use to try and get DRAND randomness out to people who want to consume it, next slide, looks sort of like 3 layers. We've got the nodes themselves at the top here. So here you can see a node representing Protocol Labs and another representing Cloudflare. And these nodes are only going to talk to the other group members. And we're going to put in place as much protection to those nodes as we can to prevent any other potentially malicious actor from directly talking to the group members, to the DRAND nodes themselves. And what that means in practice is this dashed line is really sort of a firewall in a sense, that we will try and have all of our DRAND operators implement IP whitelisting to only allow inbound traffic and connections from other approved operators and not from arbitrary external traffic. And that aims to limit the potential for denial of service style attacks against the nodes themselves, as well as making it so that some unapproved member can't start sending messages as if they want to join a group or do any of these other protocol level things and reduce the attack surface. But in creating just a sort of an IP whitelist box, we've protected the nodes to some extent, but we've also made it much harder for anyone to go and directly get randomness. So how do we then make sure that the randomness is widely distributed? So in addition to the nodes, there's a separate binary process that gets distributed either as a binary or as a Docker image or however it is consumed. The operators sort of do these deployments to some extent on their own so that there's a diversity of those as well. But these are stateless relays that will be allowed in the operator's deployment to talk to the DRAND node and fetch new random values. And these relays can be used with a CDN infrastructure to provide horizontal scaling and allow increasing amounts of client requests for randomness without having those requests directly translate into more requests on the DRAND node itself. And the main goal here is how do you think about denial of service style attacks and protect against those. Cool. So this is sort of our 3 levels. And with that in mind, we can now sort of look a little bit more deeply into the attacks themselves. Next slide. So since we've got a relay and a CDN around it, the specifics of how those 2 things work are going to be somewhat operator dependent, right? If I am to deploy a DRAND node on Cloudflare's infrastructure, the specifics of how their load balancing and CDN caching work is different from if it's on the AWS cloud or if it's in my own physical deployment. But in broad strokes, the attacks that we want to make sure that we can be resilient against, next slide, break down into about 3 things. So the nodes we should allow to not have overwhelming of requests, and that's what our IP whitelisting is trying to do. We don't want unknown nodes to attempt to join. And we want to be able to protect against impersonation. So DNS getting changed and other members thinking that a DRAND member is somewhere else or is someone that it's not. The relays themselves, we're worried about a intermediary network performing DNS hijacking attacks or blocking those IPs or blocking the specific service that is advertising itself as DRAND. And we also need to figure out a way to protect it from being overwhelmed with requests. On the client side, we need to be able to protect against false responses being returned. So if there is a man in the middle or a malicious network that misdirects a client, the client may get bad results back that have been impersonated and needs to be able to protect itself against those. And we want to limit ourselves from targeted network disruption. So if the network is injecting resets or dropping packets when it knows that something's DRAN, we want to be as resilient as we can to those style of attacks. So having laid out this sort of broad set of malicious network activities, I'm going to turn it over to Alan to talk about the mitigations that we've put in place to try and gain confidence in our DRAND distribution at being able to handle these.
Okay, I'm going to tell you about some of the mitigations we've taken to avoid network attacks, and they have the intent of boosting availability and uptime and should allow DRAND to continuously provide verifiable, unpredictable, and unbiasable randomness forevermore. Hooray! So there are a few simple mitigations that we've made to protect members of a DRAND group. Will has already covered them a little bit, but firstly, public traffic never actually directly hits a DRAND node. So to compromise a DRAND node, you need to go through a CDN or a relay or get in by some other means. But it means that DRAND nodes can be completely segregated and isolated from the outside world. And the only inbound access that is needed needs to come from other nodes in the group. And so for this, as we already mentioned, an IP allow list is in effect, and that just restricts traffic to just the IP addresses of the nodes in the group. And so finally, public API exposure is optional, so members can contribute to generating randomness without actually having to distribute it. And that just means there are fewer vectors available to attackers. Okay, so the second mitigation, failing fast with bad requests. This is about mitigating against overloading a node. And so we can define a bad request as a request that's invalid or uncacheable, or valid and just lots of them, like a denial of service attack. So valid requests for current or historic randomness round or the chain info are cached indefinitely. And since all requests are cacheable, only very few requests actually make it to the DRAND node itself, and no external traffic actually talks directly to the DRAND node, except for the other nodes in the group, as I mentioned before. So in the diagram here, we can see a path of a bad request to a DRAND node. And so a naive kind of DDoS attack can be mitigated by the CDN provider. So if we're asking for a particular historic round lots and lots and lots of times. A request for like a far future round, so a round that hasn't yet been generated, can be discarded at the HTTP relay level. And then finally, requests that try to talk directly to DRAND nodes over gRPC are discarded by the IP allow list. So we can get closer, but we aim to drop bad requests as soon as possible. Protocol Labs run a network observatory, and the idea is to measure how effective the distribution of randomness is, so its latency and its availability from multiple geodiverse sites across the globe. So this is quality of service for the distribution network, and it provides insights like some distribution mechanisms are faster in some regions. And it also provides like a baseline for what we expect the latencies to be. And so we can set up alerting to tell us when they're observed to be different and we know that something's up. We also closely monitor our portion of the DRAND network, and by monitoring randomness generation events, we're in effect actually monitoring the entire League of Entropy DRAND group. And so we graph our measurements for our infra team, but we also run a publicly accessible status page, and that could be accessed via the DRAND website at drand.love. Gossipsub is an alternative distribution mechanism, and that helps with network scaling because it's peer-to-peer communications and distribution over different transports. Libp2p can use TCP, QUIC, WebSockets, other transports to distribute the randomness. So let me first explain a little bit about Libp2p and Gossipsub. Libp2p is a modular network stack for building peer-to-peer applications, and Gossipsub is a PubSub implementation. So it allows applications to subscribe to topics, and other applications publish messages to the topic, and the message is pushed to all the subscribers for that topic. And that's all done peer-to-peer and completely decentralized. So how does this work in DRAND? Well, Protocol runs a DRAND Gossipsub relay, and it publishes randomness to a particular topic. This topic is comprised of a DRAND identifier, a protocol version, and a chain hash, and that allows other groups, so not the League of Entropy, to potentially have their own chain and distribute it over Gossipsub as well. And DRAND Gossipsub clients subscribe to that topic for the chain they want randomness from, and Gossipsub delivers randomness from any peer on the network. And so that makes it particularly important to verify the beacons that are generated, because there are many mans in the middle. So in this diagram, notice that the peers do not have to be connected directly to the main relay. So the network can scale without introducing additional pressure on the first level relay. And so Gossipsub can also provide some resiliency to DNS attacks and HTTP traffic censorship. And it's been found to be the fastest delivery for new randomness in some regions, as I said before. One experimental mitigation we have is the Twitter relay. Hooray! So it's another distribution mechanism that it could potentially mitigate against downtime or HTTP relays or block DNS to DRAND API endpoints. It is mad science. Do not use this, but let me tell you how it works. It tweets round number and signature every 30-second period. Due to Twitter character limitations, any client that were to consume this randomness would need to generate, derive the previous signature and generate the hashed randomness value from the signature. But that's okay, that's not too difficult. It's currently not useful because the account exceeds the maximum 24-hour tweet limit by only around 200 tweets. So it means that every 3 hours we miss a few beacons, so that's not good. Maybe someone knows someone at Twitter who can help with this. There is an experimental JS client that's available. I will post the link somewhere later, but that's the Twitter relay. Okay, if your application relies on getting randomness as a critical component of its operation, then you're going to need a smart client that takes advantage of this DRAND infrastructure we've been talking about. So we built two DRAND client libraries, one in Go and one in JS, and they have multiple transport implementations for you to use. So for example, you can create multiple HTTP clients for different DRAND HTTP API endpoints. And you can also create a Gossipsub DRAND client. And there's also a gRPC client, which is what the HTTP relays use to talk directly to the DRAND nodes. But anyway, multiple transports allow the client to mitigate against adverse network conditions like blockages or unavailability. And so basically, if the trains aren't running, you can take the bus. So these concrete implementations can be passed to a base DRAND client, and that allows you to consider them all as just one single client. And the base client adds speed testing and failover functionality. And the clients that it has are speed tested periodically, and the fastest client is always used. Watch channels or live feeds of randomness as it's generated, the fire hose of randomness as it were, they are automatically and transparently switched out. So we're always watching the fastest client. And that means we receive randomness as quickly as possible in the event of changing network conditions. If a client fails to retrieve randomness, then we use a different one. And the clients are ranked in speed order. So if the fastest one fails, then we move on to the second fastest one and then the third fastest one. And any failure sends a client to the back of the list. But it's okay because it can recover because we've got the speed test, and it will be speed tested again, and then it can become the fastest if it recovers. So that's awesome. The other important, really important thing that it adds is chain and beacon verification. And that means that the client verifies the chain that we're receiving randomness from is the chain we expect to be receiving randomness from. And we also verified the signature of every beacon that is delivered against the public key of the chain. And we can optionally verify the whole chain or a subset of the chain from a known trusted previous beacon. So it really makes sense to use a client library if you care about the security and integrity of the randomness values you're consuming. Finally, the base client also adds caching. So asking for the same beacon multiple times doesn't result in multiple requests to the API. It's also worth noting that it does aggregation of watches, which essentially means that multiple requests for a live feed will only result in one underlying request to the API. So that's good. There is an option for auto watching, which is for priming that cache, so that if you need some randomness later that has been generated, then it's already there for you. You don't have to go and get it. So that's also super useful. Okay, so the final mitigation, we made a bunch of important changes to the way the project operates and the systems we used. A security audit was completed by Sigma Prime. We set up continuous delivery to a monitored DevNet, and we set up automated regression testing. We have a PR approval process, so every pull request has to be built and tested and have a approving review. An automated linter runs on every pull request. We have a documented procedure for reporting security vulnerabilities. We have a documented release process, and that includes mandatory signed release commits. Our test coverage has been surfaced and is continuously tracked. And then finally, we run multiple test nets. We have a test net for the League of Entropy right now, and there's also one running at the moment for Filecoin, and that basically enables a dry run of onboarding and offboarding new members to the DRAND group. And in the case of Filecoin, it allows for like a real world testing of disaster recovery in the event of halted randomness. So that is all of the mitigations, and that is how you channel chaos. Thank you very much for listening.